Oh yeah, no, it's a change in directions that the project is going through. It's like it always happens.
Yeah.
First we're doing this, and then we're not, and now we're doing something else. It's crazy. I work for a health insurer, Anthem.
Oh, I have Anthem.
Yeah. Are you in New York? You have you're in New York, right?
Yeah, I am. Yeah, so we just got our new cards.
Yeah, Blue Cross, you have Anthem, yeah.
Well, they're huge, aren't they?
Am I what?
I mean, Anthem is huge, isn't it?
Oh yeah, I'm not even working on the New York part really. Oh. Well, I'm working on the EDI part now. I used to work on claims there, but even for claims, I was working mostly on the New England states, Connecticut, New Hampshire, and Maine. Okay. And all states are part of, but the other states are not part of Anthem. But they're still part of Blue Cross. But I've worked on the local claims for. It's huge. I mean, it's millions of members, tens of millions of members.
Yeah. So EDI, I mean, I just know sort of the basics about EDI, that it's a protocol and like it's some application framework as well, or?
I guess most people would be familiar with XML. Yeah. That's the closest thing to compare it to. It's kind of like XML. Mm-hmm. It's a markup for a document, but it's not, I mean, it doesn't have angle brackets or tags or anything. Well, it does have tags. So it's a different form of marking up a document, and there is a, like if you saw a document with angle brackets and slash angle brackets, you know right away that it was XML syntax. And the same thing with EDI. If you saw a document that had, well, typically they have stars and tildes and colons. Okay. To separate the fields. If you saw that, you would recognize it immediately as EDI, but EDI is a lot more defined than XML. So there's this ANS standards group that defines exactly how the pieces are put together, and it's not nearly as flexible as XML is.
What language do you generally code in?
Well, actually, it's WTX, so it's not even a language, really. It's Java based.
I see.
And there's C#, and I mean, there's C# and there's Java.
Okay.
It's old stuff. The C# stuff is actually ASPX. Well, the Java is Java 8.
Michael, when you say WTX, you mean this WebSphere transformation extender?
What?
Miguel knows.
What?
No, I searched. I looked it up. When you say WTX, you meant WebSphere transformation extender?
That's it. Why you
WebSphere? No, I looked it up because when you said it was Java based, I was curious. WebSphere, is that the IBM server?
Yep, I work for IBM.
You work for IBM. That makes sense. I remember back when I was, like 10 years ago. I remember that WebSphere used to be like something that I was curious if it was going to be, back then when there was a Glassfish, WebSphere, and there were several competitors. I guess right now nobody cares much about it, but I remember it was a big thing. And I was like super interested in all that.
Well, now you can go with full-blown WebSphere, or there's Liberty. There's Open Liberty and there's WebSphere Liberty.
Oh, really?
Open Liberty is free to download and free to install. There's TOMEE, and TOMEE is the Tomcat with not EJB, Java EE version of Tomcat. Has EJB too if you want to use them, but in the latest version, you set up a profile and you define whether or not you need EJBs. If you don't need EJBs, but you want to use, let's say, what is that? The REST. What is it? REST. What is it?
I mean,
JAX RS is what I'm trying to think of. Or
I
like
see. JAX RS.
Yeah, you put the pieces that you need, and the server doesn't take 3 minutes to boot. It takes 3 seconds.
Nice.
You need all the pieces.
I actually have.
So Java EE, in order for a server to be Java EE, it has to support a whole bunch of things that a lot of people don't even use, that take a long time to boot up. But,
and even worse, that most people don't even know exist.
Yeah, who knows what an EJB is anymore, right?
Yeah, I mean, I remember struggling with almost 10 years ago, more than 5 for sure, about AGBs, and finally got them. I remember it was an AGB2 that they were like a complete nightmare. And then when the AGB3 came...
They're a lot closer to what you would have as a container injection now. A bean that's just injected in the container can be an EJB, and it's no more. You don't need any interfaces. Just
but the Java world has
the only thing you need is an anonymous constructor, and I think there's ways of doing it even without that.
Yeah.
If you had to make an argument for EJB today, with competing technologies and stacks, what would you say?
The only thing you could say is that, the first thing is that you really don't need them, and the second thing is that if you do want to do it, then it should be supported as a standard across any server that you want. So the way that they work is standard. And that becomes important with the life cycle and with the sharing, the way they're injected. The way they work with your container injection. That becomes so. If you're going to stick with the same server and the same, like if you're going to stick with WebSphere, then go ahead and use them. If you want to, if you want to move, if you're going to stick with one server, then use whatever the heck you want, but if you think that there's a possibility that your application might move from one server to the next, or even your team might need to move from one server to the next on a different project, using EJBs there's more of an advantage then.
Okay, so it kind of goes together with using WebSphere as your application server.
Well, it's not just WebSphere, it's any Java EE server.
Okay.
They all have to support it, and there's a standard about how they support it. So it's the opposite, really. If you're going to stick with WebSphere or you're going to stick with Pyera or any of the other servers, then there's that reason kind of goes away. But because what I'm saying is that the reason to use Java EE, so there is another reason too. We don't build the packages from scratch anymore. We use third-party libraries to communicate with things like Salesforce and SAP. Some of them use EJBs.
Okay. Cool. I think it's just going to be us today. So let's go ahead and start. So we are still in the sorting by exchanging section 521, but we're going to finish up with these two algorithms. The first one is Quicksort, and the next is Radix exchange sort, and they have a very similar approach, but the way that they implement the approach is very different. And then, of course, if we have time, we'll do some exercises. I'll have to skip the MMIX step-through that I had planned for today because my computer on which I have the debugger set up decided to do a check disk, and it's been going on for like the last 2 hours and it doesn't seem to be finishing. So with that, let us begin. So this is page 113 through 115, which is the introduction to Quicksort. We have about 7 minutes. So there's quite a bit of material there, but hopefully we can get through most of it in 7 minutes. Okay. Who wants to give it a shot?
This is like the first true divide and conquer algorithm that we have seen so far, right?
That's a really appropriate way to categorize it.
Yeah, and also I think it's not exactly how usual is the Quicksort. Last time I don't remember exactly what was the last time I looked at it, but I think it was explained different. Anyway, it's very interesting the way he explains it. So I can take a crack at it.
Mm-hmm.
Basically, what you want is start with some number, with some key, and in this case, he starts with the first one because why not? And say, okay, let's find out where this key is supposed to be, right? And by doing that, what it suggests is, by the way, this Sedgwick name is the same of the Coursera course and the algorithms book, or is somebody else?
Well, yeah, he does have a very famous algorithms textbook. I think it's just called Algorithms.
Yeah, it's algorithms, and
right.
Has a Coursera course too, right?
I'm not aware of the Coursera course, but you're probably right. I'm sure that he must have one. He is very famous. That textbook, it's been a while since I looked at it, but it was very famous for the illustrations where it used this graphical stick sort of graphic where sticks are tilted in one direction, I think. It was kind of like that. And then they're kind of mixed up when they're unsorted. And then when they get sorted, they're all leaning towards one direction. So it was like a nice visualization of that.
I didn't buy it because it was in Java for some reason.
Okay.
Anyway, so he starts with the first element. So he says, let's take two counters, one is starting in 2, and the other one is the n, the last one. And so we are going to compare everything with the first item of the list. So that's why it starts in I equals 2 and j equals n. And it's going to start moving the I and the j. So I was going to increase the i's and start looking at each element of the next I, comparing it with the R1 in this case with the first element, and the same with the j's as they decrease and the i's are increasing. Trying to figure out if each of those elements corresponding to the i's and the j's will go to the left or to the right of the current element, in this case, the first one. Once the a's and j's, every time we find one that should go to the left of j, they swap. Every time we find one that should be to the left of R1, we swap j's and j with I.
And what's the criteria for something going to the left?
So we are talking about the R1, so the first element. Mm-hmm. If that element is less than Ri, then then Ri goes to the right. Therefore, right? Yes. So to the left goes all the elements, all the items that are less than R1 in this case, or the element that we're looking at. And to the right goes everything that is bigger. So as we keep going, we are swapping i's with j, the element corresponding to I with the element corresponding to j if the I is supposed to be is in the wrong place.
Okay, I think that you've described it really well. Could you walk us through table 2?
Yeah, table 2. Yeah.
Or maybe even the one before on the previous page.
One before,
where he shows one pass.
Yeah, that's a good idea. Right. So in the initial file, it's fine. I call files to the arrays. Mm-hmm. So in the initial file, we have just the 16 numbers.
Yeah.
And I would be 87, which is the second one, and J is 703.
Yeah.
So 87 is supposed to be to the left of 503, which is the first one, so it stays in place. 703 also supposed to be to the right, so it stays in place. The next pass, I will increase I to 1 and decrease j. So we increase j. Let's start with I. We increase I, and we find that I is 512, which also supposed to be to the right, so it's in the wrong place. And in the case of j, we keep going, increasing j until we find 154. That is the one that is supposed to go to the left of 503, which is the first one. So when we found those two, we swapped them. And so in the third row, we see that now when 512 was, now we have the 154, and when the 154 was, now we have 512. So basically, you decrease I until you find the wrong one, and you increase I until you find the misplaced number, the misplaced key, and you decrease j until you find the misplaced key. And they don't need to decide. You just keep going until you find both, right? And then you swap them, and so on until you can't swap them anymore. And then 503 will remain in this final position. And the goal now is to do the same thing with the two halves that you end up with. Okay. I jumped the next two steps because it seemed obvious.
Yeah, that's right. And then table 2, how is table 2 different from this first?
Well, it just adds the idea that you need to keep track of. So that he says that you want to. So in table 2, in the second row, everything is already. So the first, what we just described in the previous table is essentially just the first step in table 2, right?
Yeah.
So you end up with the two halves, well, not halves, the two partitions with 503 between them. So now you pick the smaller one, which is the one that from 1 to 6, and you do the same algorithm to it, right? Until it is completely sorted. So you keep in the stack the other half that you have, right? In this particular case is kind of weird because in the second half, the second half gets sorted immediately, so you don't have any more stack. But yeah, it's essentially somewhat recursive. Somewhat, it's totally recursive algorithm, just going half by halves, doing the same thing. Partitions are partitions. I just stop saying halves. They are not halves. They are partitions.
Yeah, that's right. Michael, any comments? You're muted, Michael.
Okay, a little bit of display lag there or something. It wouldn't pop, the unmute button wouldn't pop up. The way I understand the first table, okay, which is really the process that you apply over and over again, I sweeps over. So we're going to look at the first element, and that's going to be the one that we're going to put in its proper place. And in order to do that, we have to find its proper place. I sweeps over the elements that are less than the first element. J sweeps over the elements that are greater than the first element until it can't. So I moves over to 2. Well, on the first, on 087 is less than 503. So we can move beyond that. And then we get to 512, which is greater than. Remember, I wanted to let I sweep over elements that are less than. So it stops. I stops at that position 3. and we look at J. J decreases past 703, 765, which are all greater than until it comes to 154, which is less than. And now we have 512 is greater than, we want an element less than, and we have 154 is less than, we want an element that's greater than. So we just swap them, and then we continue on. I think that's pretty clever. So in the end, I and J eventually cross, and when I and J eventually cross, we know the place where the 503 belongs, and we just swap it with whatever I guess we swap it with one of the elements.
With J, with yeah. J, with some whatever was at J, because that's the one that's
less than, right?
Less,
J,
yeah.
J was sweeping over elements that were greater than. When it comes to cross one that's less than, but I is already past it, we can't do the swapping trick anymore, and that's where the 503 belongs.
Yep.
Mm-hmm. Yeah,
that's right.
Yeah, that's the way I understand the first one, and you're right. The second table, it's not a really particularly good example because the stack only gets one element, which is kind of weird. I would have expected that you would get more than that, but it's just the way the data works out. I think here's a mathematical question: how many combinations out of the 16 factorial combinations of ways of ordering 16 elements? How many of them require a stack depth greater than 1?
Yeah.
That sounds like a Ruth problem. It may not have an answer.
Okay, so that's great. Let's now look at the actual algorithm. So that just follows. So we'll just do the algorithm and then the accompanying flowchart in figure 19, pages 115 through 117. 7 minutes for this. And I do want to point out step Q7 in the algorithm. It is quite involved. So what I'm going to do is I'll put up a slide that's broken out the various pieces of step Q7. So I'll leave it up here, and when you reach step Q7, you can look at it. I think it'll help you break down what's happening in that step. So we can start. Okay, did everyone get past step Q7?
I'm right there.
Okay, we'll give it another 2 minutes maybe. All right, I'm going to put up the slide back up so then we can really focus on it. But let's just discuss what we got out of the algorithm and how it sort of maybe differs in your view or clarifies things compared to the initial description.
Well, to me, it seems to add two things. The first thing is he has this big M parameter, which is probably supposed to be set to some smallish number like 4, 5, 6. And when the subfile that you're sorting gets smaller than that M, you're not going to apply it. You're not going to use the quicksort. You're just going to use this insertion sort. That's the first thing that's built in, and that's a couple of steps here, and that's the reason why 7 is so complicated. And then the second thing is, once you've finished one stage, you now have 2 subfiles. You've got to put one subfile on the stack, and you've got to sort the other side. And how do you decide which side to sort? Apparently, in this algorithm, he's just taking the smaller of the 2 subfiles rather than always taking the left or always taking the rather than the largest of the 2 subfiles.
I think he did mention that before the algorithm somewhere.
Yeah. Okay. Well. Yeah. Okay. Well, that's not really part of the quicksort in my mind. I mean, it may make it work better, but those 2 pieces are built into this flow chart, which is part of the reason why it's so complicated. That may very well make it work better. But I don't think they're necessary.
Miguel, what do you think?
I'm confused by the Q7 still. Why is this adding? What is this using J in the left side? I'm trying to figure that out.
J
is
on the
not
left.
I anywhere?
R minus J is the size of the right subfile, and J minus L is the size of the left subfile. So what we're saying here is if the right, in the first branch, we're saying if the right side is bigger, we're going to insert the right, we're going to put the right side on the top of the stack and continue with the left. And then the next if branch is saying if the left side is bigger, then we're going to put the left side on the stack and sort the right. And then the otherwise have to do with if the subfiles, if either of those subfiles is smaller than that M parameter, we're going to do.
So I think I understood that was what it's supposed to be doing, but what I don't understand is how it's doing that. So, for example, let's go to the first comparison here. Like if R minus J, that makes sense to me. So R is the extreme right, J is the index that is decreasing. Therefore, when you subtract them, that's the length of the right.
Sorry,
but how about the other side, J minus L? I don't get that.
Miguel, this step is after J has crossed I. So J is now where you've placed the pivot key.
Right.
J is now fixed.
I see. Makes sense. That was the missing part.
J is the separator between the two files. That's where you're going to put the original K.
Got it. Yeah, everything fall into place now.
Okay, great.
Yeah, and as Michael said, it's this M that is making step Q7 so complicated. Well, it's not just that M, but it's the M and the choice to only put one of the partitions on the stack and continue with your loop with the other one, which is very interesting. I'd never seen this before.
Yeah, I think most of the time I've seen Quicksort implemented, when you get to step Q7, it just puts both of them on the stack and goes back to Q2 where you would pop one of the elements off the stack and apply the algorithm. So Q7 could have, if you're trying to explain what Quicksort does, Q7 could have been just a single line. Put them on the stack.
Yeah, you're right. But what's the advantage of doing this as far as he explains it?
Well, there's a big advantage in not manipulating the stack so much. And like you see, when that algorithm is applied on table 2, you only ever get one element into the stack. And he's also choosing. There must be a reason for it, but he's also choosing not to push the small element onto the stack. Maybe that's so that he can drop down and do the insertion sort. As you know, when the smallest element gets smaller than M, you can drop down and do the insertion sort. And I mean, I don't really have an intuitive feel as to why he wants to greedily sort the smallest subfile first.
My feeling is that he's picking the longer partition for the stack because we're already working on one partition. Yep. And you know, if we just stick with the shorter partition, we've paid some overhead for dealing with the original partition and whatever it is. And so if we just continue with the shorter partition, I think the idea is that we won't be paying as high an overhead as with a longer partition, right? We may get to the shorter threshold length a little earlier within this current invocation. And so that makes a little more sense to me. If you had to pick one, then defer the longer one, because then, you may be doing a bit more work with the longer one. And for that, I guess paying the overhead of putting it on the stack may be worth more. Yeah.
Or it might just be that we can avoid putting, if the smaller one ends up being smaller than M, we can avoid ever putting it on the stack by following this algorithm. So if we find those, then we've decreased the number of things that we have to put on the stack.
Yeah.
That seems to be it.
Yeah, and as far as only picking one, he has an exercise that I haven't looked at, but he says then the depth of the stack that you'll need is bounded by log of n.
By only picking one?
By only picking one, yeah.
What does only picking one mean? Always picking the left?
No, I don't think he says that. I think he says just the fact that you're only going to put one of these partitions on the stack.
Oh, got it.
Yeah, so I think that is... Where does he say that? Right in the introduction to the algorithm. In the second sentence, he says an auxiliary stack with at most log base 2 of n, actually the floor of that, entries is needed for temporary storage. And I believe that he mentions that this is some exercise, but I don't remember where it is exactly.
Okay.
But yeah, so that's really cool that there are these couple of optimizations. The other thing that I found very interesting was that the insertion sort threshold, that's being applied to every single partition that we come across. But the actual insertion sort is being run on the entire array at the end. So it's not applying insertion sort on every little piece that it encounters. It's saving it till the very end. That's my understanding.
Oh, you're right. I think you're right. Yeah.
Yeah.
That's why take off the stack when the stack is empty. It has to go through Q9. Q8, take off stack. If the stack is empty, you still haven't done any of the straight insertion sort, so you have to do Q9. I was thinking, I'm thinking the classical way that I learned Quicksort was you always put things on the stack and then you take one off, and when the stack is empty, you're done. But this is when you take it off the stack and the stack is empty, you still haven't done any of the Quicksorts. Got it. Or
so
any of these.
Yeah, go ahead.
Yeah, or rather any of the straight insertion sorts. You're going to do the insertion sort on the whole file, but you're never going to find more than M elements that need to be swapped. Interesting.
Yeah, it's very interesting. I guess Michael got disconnected. We can give him a couple of seconds to reconnect. Miguel, what do you think? Any comments or questions about that?
The only comment is that I don't understand why. I mean, it seems like the Q9 and the M thing is an optimization, right? Wasn't him, Knuth, the one who said early optimizations are the root of all evils?
So that's probably the most famous quote attributed to Knuth. I really don't know if he actually said that, but it's very interesting to me that quote. Michael, you got disconnected. We were talking about this famous quote that Knuth has said to have said about optimization. Miguel, what is it? Could you repeat it?
Well, the one I have in my memory is that early optimization is the root of all evils, or something like that. And it seems to me that, so what I was saying, the reason why it said that is the Q9 and M seemed like an optimization to Quicksort in this case, right? As you said, Michael, like obviously if you just, actually not just you, like Knuth himself said, if M is equal 1, therefore you just sort the whole thing using Quicksort, right? Which is what you said, which is the equivalent to the one you said where the stack is empty, you're done, is the case when M is 1, right? So increasing M and then using insertion sort to sort the last partitions is an optimization, obviously, right? So I'm wondering why introducing optimization while introducing Quicksort. So what's the whole point? What's the point of that? I guess I will find out, but no, it seemed interesting.
Do you have any comments on that, Michael?
Well, I wonder how closely this algorithm follows what Sedgwick wrote in his paper that Knuth quotes. And also, optimization, early optimization, that means like before a program is developed, a programmer chooses to do something more complicated because it's going to be faster or slightly faster. I can't tell you the number of times that I've seen somebody do something crazy because it's faster, and then you look at it and you see that this particular piece of code is going to save a few hundred milliseconds and it's going to be run once a day. So, I mean, how good is that? Yeah, you saved 100 milliseconds, and over the course of a year, you're going to save maybe 30 seconds of runtime.
So I'm trying to predict the next few pages of this, right? So what I think is going to happen is that he's going to say, look, when we increase M up to a certain number, that's probably going to be some analysis about what that number is supposed to be. The performance is significant, the improvement. Although, to your point, if we try to find like a parallel between this and real life, like a PR, right? And somebody is introducing the equivalent of introducing Quicksort to this algorithm, I would tell them in the PR, don't, just leave it, leave it out and see what happens, and then we can introduce the insertion sort thingy. But I'm guessing that we're going to find out on the analysis of this algorithm, how was the real impact of M, right? Which is something that you won't find in the PR. So in the PR, nobody's going to give you like a detailed analysis of why you have to make it more complicated. Nobody's going to read it anyway. So Michael, I was saying that we supposedly we're going to find out in the analysis of this algorithm why M is so important.
Yeah, maybe.
Yeah. So these are all great points. It does make me wonder about that quote, because it's certainly not something that I would have thought Knut would say after reading, so much from TAOCP and closely reading and trying to understand it. Every single algorithm that I have seen so far, from the simplest ones, have some sort of optimization from the very beginning. And, so his presentations, go ahead, Michael.
They always count down.
They always count down. So,
and
so
that's an optimization that has been called out as one example of, especially C programmers are trained to count down instead of counting up. And the brain naturally thinks of counting up to the end of the array. So that's an example of an optimization that saves a very small amount of time, but everybody does. And it might be evil because you're not, when I read the Knuth algorithms, I get caught by that all the time, that he's counting down. It makes me have to think about it more.
Yeah, so those preferences are certainly there, but what I am referring to more is bigger algorithmic optimizations. So, for example, in bubble sort, in the simple bubble sort algorithm, he introduces the bound, which you don't really need, but it makes a big difference. And in every single algorithm, I've noticed that even the basic ones that he'll present that will be often refined, they usually start out with some clever technique that's built into the basic algorithm. And one of the reasons why I think that he does this is that all the algorithms and all the optimizations and efficiencies that he's mentioned, they generally originate out of some paper. So, you can imagine like there was some initial bubble sort technique, right? But then people improved upon bubble sort. They proposed various refinements, enhancements, efficiencies. And when Knuth is presenting sort of the first take on an algorithm, he'll usually distill a bunch of papers and he'll present it together with some optimizations that I think he feels are so basic and so fundamental that they improve the algorithm so much that you really should not you really should not be avoiding these optimizations. And then there's more sophisticated ones that he'll refer to in further discussions. But that's one of the very interesting things that I've learned, and that's why I think that he's done this with Quicksort as well. He does mention that where these optimizations for a single insertion sort at the end, which paper this is coming from, and anything else that he'll add to the basic algorithm. I think they have origins in some work that's been done by researchers over the years. Okay, so Miguel has posted the quote, and we can look at that later. Let's just quickly look at the actual MMIX program and see if there's any questions that arise out of there. Spend about 5 minutes on that. Okay, so it's about 3:09, so let's take a break till 3:19. We'll come back and continue. See you. Okay, we're back.
Hello?
Yep. So, anything to talk about on the program, the MX?
No, I just read it until line like 10, and then I had to use the break. So
No comments? All right.
Comments. Anything I say would be used against me.
Okay, so let's go on to the analysis.
Yeah.
And the analysis has a little piece in the supplement as well, but most of it is in the main text. One thing I'll point out: there's a lot of pages here for the analysis, but if you look at page 119, the first paragraph of page 119, at the end of it, he says, however, non-mathematical readers are advised to skip to equation 25, which is a couple of pages down. So, you know, you can go through it, but a lot of the stuff can be skipped. And if you continue from equation 25, he talks about the calculation that you could do to figure out a good M value. And then he has some refinements after that. So anyway, we have about 7 minutes till about 3:29.
No, we didn't see that.
Okay. I don't know if Michael's still here. Michael, are you there?
Yes, I am.
All right, cool.
My camera apparently doesn't like Google, or Google doesn't like my camera, or something.
No problem.
Are you using Firefox? I had to switch to Brave to make things work.
Okay, so what's your takeaway from the analysis?
Well, other than M is significant, I mean, obviously we skipped all the parts where we're supposed to understand how significant it is, or how we figure out that its significance.
Does it provide a way to figure it out?
Well, it provides a formula, and eventually an actual number. So there is a formula, but still, the derivation of the formula is what is, swept under the carpet for now. In Formula 2025.
Right.
The funny thing is that Quicksort still is quadratic in the worst case.
Right.
And he claims, no, we know that one way to make it not quadratic is to combine it with other things. Right.
Okay. What does he suggest?
What does he suggest? I mean, in the last few paragraphs, what does he say? So, I mean, other than adding in insertion sort, I'm not sure, actually, I think insertion sort doesn't change anything. I mean, what does it actually says? This depth partitioning thing, where what I don't remember. What was algorithm 523? Is that the insertion sort? I don't remember. 523.
I think that is
not there yet. It's in the future.
523. We haven't covered it yet. Yeah.
We haven't get there yet. Yeah, it's something that is in the future. So you combine it with the future algorithm.
Mm-hmm. And how do you switch over?
So when any given subfile has been subdivided more than they say 2 log n times, right? So I guess we have swapped over and over and over for that number of times. So you started with one big file, right? Then you divided that one in 2. Then one of them is divided in 2 again. Then divided, and if those division has been that number, 2 log n, log n, then we switch to this secret algorithm into 523H.
So if we have an array of size 100,
right,
then log base 2 of n.
That's 2, right?
No, so that'll be 2 to the 6 is 64, and 2 to the 7 is 128. So it's, somewhere between 6 and 7. And so let's take 6. That means 2 times 6 is 12. So if we have subdivided that array of 100 elements more than 12 times, then we would switch over to. That seems pretty excessive. I wonder if the threshold really needs to be that high, but I guess there's some proof associated with that it will guarantee the n log n worst case. So yeah, that's definitely interesting. Michael, any thoughts or comments on the analysis?
Yeah, I'm reading the analysis in the main volume, not not the one in the MMIX. But the M value on the two came out to be 9 for the older computer, the older mix,
yes,
and 12 for the MMIX, which I thought was interesting. So that leads me to the question: what is it on the Pentium? Tell me something useful. I guess you'd have to have an algorithm first.
You may want to Google it if I'm sure that this formula is coming from some paper, or at least, it's been well known if Knuth is the one who actually derived it in the first place. My feeling is that it may have been Sedgwick, because Sedgwick is supposed to have done a lot of work on Quicksort. So if that's the case, then there may be published numbers for all the well-known architectures.
I think I've seen sorting libraries in Java where the M, where it was converted over to a straight insertion sort, was about 12 or 10 or something like that.
Okay. Yeah, should be an interesting exercise. Any comments on the selection of the pivot, the element that everything is going to be compared to?
That's another thing. I've seen implementations where the pivot is chosen from the middle of the array, and in the volume 3, he says one of the suggestions from Hoare was to select a random element. And another thing is, in reality, a lot of things that are applied to your sort function are kind of somewhat ordered, which is very bad for the quicksort as it's described here, because I think the more that the algorithm performs the worst when you give it something that's already ordered. Hmm. And I think, I don't know, like if you give it a list or a file to sort that's almost in order, is that going to be bad? Maybe not necessarily. I don't know.
So I don't remember, I think it's in the Sedgwick Coursera course. I don't remember which algorithm, probably was this one, where one of the first steps was to shuffle the algorithm. Maybe it's something totally different, has nothing to do with this. But I remember there was one.
That's interesting. So what you're saying is that whatever the original ordering was, you just create a random order on it.
And shuffling is only order n.
Yeah, exactly. So it's not expensive. Yeah.
That should work very well, actually.
That's pretty funny. All right. Let us move on to the next algorithm, which is Radix exchange. This is also a partitioning kind of algorithm, and it swaps elements if it can find them, but the way it does it, the criteria is very different. So we have till about 3:45 to read. Okay, who can explain Radix Exchange and maybe walk us through table 3?
So I don't have enough intuition to explain binary stuff. So I'm just going to comment to Michael's points before that in this case, he says at some point in this algorithm, we don't going to choose the smaller subfile because we don't care about because the stack will never grow too much. I didn't get why it won't grow too much, but I just said that. So that means that the whole point of picking the smaller subfile in the previous queue was to keep the stack smaller.
How does it work to sort? Why does it actually end up sorting?
I don't know why it works. All I see is that it's doing something similar to Quicksort. The only difference is, the big difference is that it's not it's like doing several passes based on each bit of the numbers. So it's using binary. So it's using the binary representation of the keys, and then it's comparing. First, it's comparing each bit. First, it starts with the first bit, leftmost bit, right? Is the leftmost? Yes.
Yes. It'll start with the most significant bit, right? Which is the leftmost bit.
Right. So it tries to put all the zeros to the left and all the ones to the right.
Okay.
When that's done, we move to the second bit and try to do the same thing in the division, in the subfile, when everything is 0, then compare it, do the same algorithm, but using the second bit. That will move all the keys that the second bit is 0 to the left, and all the items with the second bit is 1 to the right, and then do the same to the left, do the same, and so on to you. I think I didn't get the last step, but it kind of makes sense.
Okay. Michael?
Right.
Go ahead, Michael.
No, I don't really have anything.
Oh.
I mean,
shall we go through table 3?
So on table 3, on the first stage, you're sorting by the bit in position 10 because you know ahead of time that these are 10-bit numbers. So that is actually quite easy to read. It's the numbers that begin with, because these numbers are all in octal, the numbers that begin with 0, we want to put them on the left, and the numbers that begin with 1, we want to put on the right. So you sweep your eye from the left to the right, and you stop anytime that first number is a 1, and you sweep your J from right to left, and you stop anytime the element that you find is 0. So doing that, on the left side, you find that 1000 in column 3. He doesn't number these columns, which makes it hard to explain. And on the right, you find 0775. And so I is still less than J, so you swap these two numbers. And then you end up with what he has on row 2. Well, on row 2, he's carried that sweeping further. you get 1614 to be swapped with 232. And then you get the 1601 to be swapped with 0652. You're always swapping a number that begins with a 1 and a number that begins with a 0. Then when you get into the second stage, in the second stage, you have on the left side there, you're now swapping something that you're now looking at the second bit. So you're going, because on that left subfile, it doesn't matter which subfile you're on, the leading bits are always the same. They'll always be 0 on the left-hand side, and, well, when you get further down, it might be 0, 0, or 0, 1, or 1, 0. But on the second stage, you're looking at the second digit there, which has to be greater than 4, 5, 6, or 7. Those are the possibilities in octal that have the first bit set. So the 767 is out of place because it's greater than, the 7 is greater than a 4. And then when you start on the right, 0423 is okay because we're on the right side and we want that bit to be 1, but we find 0652. No, it's not. 0652 is greater than 4. 0252 is the one that we're going to swap. So we swap 0252 with 0767. It works a lot like Quicksort. I don't really understand the 16,2 in the stack, but the comma 2 I think means that subfile is waiting to be sorted on the second bit. But why is it a 16? I don't know.
So I think those are the values for L, the new L and R. No, sorry, not L and R. You only need R because L is always the same. The second parameter is the bit position from the left.
Okay.
So the first stage.
Yeah, I got the second one, but what? The whole thing is 16, so you're saying we don't need the L. Why not? When we pop something off the stack, how do we know what L is? Well, whatever. He's optimized it out.
Yeah,
I would have thought you put L and R onto the stack, and you also need the bit position, but he figured out a way that you didn't need one of them, so save a byte. Save a byte, make people who want to read it spend an hour.
Okay, let's look at the actual algorithm now.
Guys, I need to drop off.
Okay.
I think we are not doing it on Christmas. So happy Christmas.
Yeah, so that's actually a good question I did want to ask you. So we'll skip December 26th then?
Sure.
Yeah. That's
okay,
fine.
And what about after New Year's, the 2nd of January?
It works for me.
Works for you? Yeah. How about you, Michael?
Fine with me.
Okay, so I'll schedule it for the 2nd, for the next one. And that'll be mostly on Mergesort.
Brilliant. We got there.
Okay. Michael, can you stay on?
Yeah, I can stay.
Okay, cool. So, all right, so let's go on to the actual algorithm. And about 7 minutes on that till just about 4.
One thing about this algorithm, what happened to M? Why was it needed? Why was it needed in Quicksort and it's not needed here? Wouldn't the same logic apply?
Oh,
but you couldn't do it in the same way because of the way he eliminated the L out on the stack, I'll bet.
Yeah, for some reason, with this algorithm, you don't need more than log n depth anyway, because you're going on the bits, and the bits are log of n. And so that's why he explains that the maximum depth that you'll need is m minus 1, where this is a small m, which is the number of bits in the number.
Okay. I'm kind of unconvinced that using some m might not help you. Like if you're down to the very last couple of bits, then your insertion sort would be on, if these are all different numbers, you know, what I'm saying is that I think using a value of m and then going down to a straight insertion sort, it's probably going to help at some level for the same reasons that it helped on Quicksort.
It might, but I think that one of the motivations for adding the threshold is the amount of work that you have to do for Quicksort in the comparisons for the various choices, right, after the pointers cross.
So in Quicksort, you're just comparing an integer to an integer. In this one, you're masking off a bit and comparing the bits.
Mm-hmm.
Isn't this comparison actually a little harder? Just saying.
Yeah. I have a feeling that it would be faster, but yeah, maybe.
Oh, okay. He's ordered the stack so that the last thing on the stack is the rightmost. Instead of in Quicksort, we put the smallest of the two on the we executed on the smallest of the two subfiles and put the larger of the two on the stack. And this one, he's putting the rightmost guy onto the stack and doing the leftmost.
Yes.
That's why he doesn't need to put L onto the stack, because when he comes out, he's done the rightmost subfile. And so you just set L equal to R plus 1 in step R10. But you could have done the same thing in Quicksort, in algorithm Q. So they both do different optimizations that accomplish different things. And I'm not saying that they're not the best optimization to do, but they're both optimizations, and optimization is the root of all evil. You don't need either of these optimizations to understand the algorithm.
Yeah, but again, I think that the way he presents things, it's not just that. He's presenting, again, the efficiencies that people have found that make significant differences. So,
okay, but he's not describing that. Well, he did describe it for M, I suppose, but not in the, okay. All right, I'll accept that. I mean, he did it for M in the Quicksort, but then there's no explanation of why we don't need M in the Radix sort.
So I don't know if this helps, but just before the algorithm, the very last paragraph of the general description, He says, as in Quicksort, we can use a stack to keep track of the boundary line information. And then instead of sorting the smallest subfile first, it is convenient simply to go from left to right. So do you think that that helps explain?
No.
No?
I said that in Quicksort, that you could go from left to right, or put both things onto the stack. Mm-hmm. That doesn't say why it's... What I'm wondering is, why is it better to take this shortcut in algorithm R when we had to do the smallest first in algorithm Q? I don't see any explanation of that. I'll accept it that, you know, especially if this is coming off of papers from computer scientists like A.C. Hoare and who is Sedgwick. Mm-hmm. Yeah, if it comes off of people who study this, I accept it, but I just don't see the reason. And there may not even be a reason. It just may be experience, I suppose.
Right. So the question that you're asking is the same left to right ordering you feel could have been used in algorithm Q as well, and not have to.
Quicksort algorithms back when I was studying, you know, back when I was taking my master's degree, and the way I remember doing it is putting both subfiles on the stack, and then at the step where you begin a stage, you pop one item off the stack. So you begin the whole thing by putting L equal to 1 and R equal to N onto the stack. And then you go into the algorithm. The first thing you do is pop something off the stack, find the two subfiles, and put them both onto the stack, unless one of them is empty. That's the way I remember doing it.
Yeah, I think if you just wanted to explain the concept, the fundamental concept behind Quicksort, that's probably how you would explain it. But I think that he's just incorporated some significant improvements from the very beginning. So yeah, it does make it a little difficult if you're thinking of this as the basic introduction to what the concept is for Quicksort. That's not the case. And again, as I said, I don't think that's the case with any of his algorithms that he's presenting. I think that's what makes TAOCP different from other algorithm texts and worthwhile, in my opinion.
Okay, so now So now I understand that stack, that stack. I didn't understand the 16, which was the last element. So you have 16, 2 in that first row on table 3. That just means that wherever we end up when we finish the left-hand side, we're going to end up doing something with 1 through 7, is it?
So we'll have moved L to a point where it can start acting as the left for the other things on the stack.
What I'm saying is, when we pop that 16, 2 off the stack, the thing that bothered me is that I wanted to know what the left part of that subfile was. I know it ends at 16, but how do I know? Because I'm just popping it off the stack, and then I'm going to begin working on that subfile. How do I know? And it's the way that the algorithm is laid out. The step that I just completed will be something up to 7, and I know that I have to start at 8 and then go to from 8 to the number in the stack.
Don't you feel that do you feel like one of the key things to understanding this is the fact that number one, we're only putting one side, which is the right side, onto the stack, and then we're going to finish up the entire left side before we get to anything on the stack, right?
Yes. Yeah, sure. Yeah, sure, but it's more than that. It's we're arranging it so that we're doing things from left to right. So when we finish the left-hand side, the subfile that we just finished ends one before the item on the stack that we're about to pull off.
Yeah.
That's important.
Yeah, it is. It is. It is. And again, it's very interesting. Like, it's a very subtle thing, but you really have to understand the whole thing before you can understand like so an earlier decision.
In algorithm Q, we put when we popped an element off the stack where the left-hand side is, because we've just finished the smaller of, it could be any point on the left-hand side that we finished. It wouldn't necessarily be the one immediately before the element on the stack, but because that could have been the smallest of the next subdivision. So in other words, I'm saying that if this was 16 files and you did, on your first pass, it was 1 through 7 is only 7 elements, and 8 through 16 is 9 elements. So you do the 1 through 7 first, but then it could come out that the next time, the next subfile goes from 1 through 5 and 6 through 7. So you do the 6 through 7 part. I'm ignoring M, and now you do the 1 through 5 part. And then when you finish with that side, you don't know. You have no way of knowing what the left. So you pop the 8, 16 off the stack, but if you didn't have that 8, you wouldn't know where to begin.
So I think that in my mind, and this is probably what you're saying as well, in my mind, the key difference is that the partitioning in Quicksort is based on one of the keys, right? And we're just ordering things relative to that key. But among the things that are being ordered, there's no relationship, right, within each partition. Whereas here, when you partition on a bit, you're pretty much saying that everything to the right, we know that this has the 1-bit set, or the bit is set for everything to the right, and the bit is off for everything to the left. And so when we are putting the right partition onto the stack, we're saying something about this group of numbers compared to all of the numbers before in the left partition that's kind of independent of any single value, right? I don't know if this makes sense, but I think that's why this mechanism won't work with Quicksort. Because with Quicksort, the decision is based on a particular key.
But in this one, it's based on a particular bit. I think it would work. I think you could do this the same way that you did Quicksort in terms of, like, for instance, always working on the smaller or always working on the larger of the 2 subfiles. It would work. But if you did it with the larger and the smaller, you'd have to modify the algorithm so that you put both L and R onto the stack. I think that would work.
No, I'm asking about the other way around. Applying the right partition selection or that choice to Quicksort.
You would have to do the same thing with when you pick which subfile to sort, you would have to always pick the leftmost one. And then it would work, because when you're finished, you're finishing the rightmost one, and the next element on the stack, that from the stack, you know where the new R is, and from the element that you just finished, you know what the new L is. The same way this one works. I think that would work in Quicksort. It might be worse performance, especially when when would it be worse? It might force you to into a situation where you're let's see. I guess it would be worse when you have, I don't know. If you're always doing the left one first, and the left one is always larger, that might be a worse performance. What would that be? That would be the case where it was nearly sorted. Maybe doing it the way he's outlined it here would work. Remember, I talked about how does this? We know it performs bad when the items are completely sorted, but how does it perform when the items are nearly sorted?
Hmm.
And nearly sorted doesn't have an exact definition, but I can tell you from experience that when you're sorting a file, many times the file is already, there's a lot of order in it.
Yeah.
Not like a lot of times it's like all of the items from day 1 through day 5 are already sorted, and you're adding in new files from new transactions. So at the end they're not sorted, but at the beginning they're completely sorted.
Hmm. Yeah, that would be, I wonder if there are exercises about this, applying one or the other technique to the other algorithm.
I don't know.
Okay,
anyway,
so, yeah, go ahead.
Anyway, now it's clearer to me. I mean, we're nitpicking about the different ways of picking which half to work on first, or how the stack works, but I think I got a handle on it now.
Okay, great. All right. So we did the discussion of that. We'll skip the program, but let's look at the analysis afterwards. Page 126.
Through 128.
Yep. And a little bit in the supplement if you're interested.
I'm not really going to have time. I've got some time yet.
Okay.
I'm wondering how useful Radix exchange sort is when you have long keys. And long could even be like I'm sorting things by last name, which I'm kind of working off of the comment at the bottom of page 127. It is important to note that our entire analysis is predicated on the assumption that keys are distinct. Radix exchange sort is as defined above is not especially efficient when equal keys are present, but it's also not especially efficient when if your key is a string and the first n bytes of that string are identical, but you've got a difference in the end. Like if you're sorting a file by name, you might find a lot of people that have the last name Smith, and you want to put all those Smiths together, and then Michael you don't find the difference until you get past the last name part of it.
Yeah.
And that would mean that your Radix exchange sort, even if you only had 100 items, you'd have to go through all of the bits for the last name before you even found any work to do.
Yep. It probably works better if you do have keys that are actual numbers.
And what if the actual numbers that you're sorting by are floats?
Yeah.
It's probably a way to make it work, but if they're floating point, you can't just use the bits. There's probably something else you could use, though. You could probably, I guess you would be using the logarithms. You'd have to normalize the floating bit point. do some kind of computation like that, you could probably do it.
I suppose you could convert them to some.
You could probably make it work with floating. I think you could make it work with floating points.
Don't you think that you could represent the floating point number as some fixed point format and then apply to that?
That might work too. Yeah. As you mean, like, yeah. I don't know. It depends on the distribution of the floating points. Like if the floating points were all in a range between, let's say 1 and 2, that would probably work very well. If the floating points were a range between 0 and 1, it would be kind of hard because you might have some that are very near 0.
Yeah.
There might be a good way to do it, though. I could see that. So on page 127, he's actually talking about sorting real numbers with Radix sort. I love it. Case 2, which is the real number, is comparatively difficult, so it has also been left as an exercise. Okay. That's interesting. Remember the comment I made about in Quicksort, you're comparing a key, but in Radix sort, you have to mask and compare a bit. So instead of just comparing a key, you have to mask and compare a bit. But actually, maybe you don't. He says, so maybe you don't on the innermost loop. You can make a fake key that is the bits that you've done so far plus a 1 in the position that you are doing in all zeros. And then anything that's greater than that artificial key goes to the right. Anything that's less than that artificial key goes to the left. So you don't have to do all of that bit masking. You can mask, you can make a key. I wonder if the MMIX algorithm is doing that.
Yeah, that's a good point. So you can turn the bit check into a kind of comparison.
It could be a comparison instead of a bit check. So, but you still have to make that artificial key. So like in the very first pass of the algorithm, your artificial key would be 1 followed by all zeros.
Yeah.
And then when you're doing the left subfile of that, your next key would be 0, 1 followed by all zeros. And then I guess the next one that comes out in that table would be 0, 0, 1 followed by all zeros, which you could do by one bit masking operation per loop, per subfile, instead of 1 per element that you're comparing. A lot less. That might actually improve what he's got here.
Well, in the MMIX code, in the supplement, I do see an AND. So I think that he is actually masking.
For each comparison. Maybe it doesn't make a difference. What is he ANDing? He's ANDing that bit. If AND is taking the same length of time as a compare, then it doesn't really make a difference. It's the same thing.
Yeah, it's the same thing. It's AND versus compare. That's all it is.
Interesting. All right. Okay, my wife is coming. I have to go.
Okay, well, thanks, Michael. And
thank you for hosting this.
Huh?
I said thank you for hosting this.
Oh no, that's my pleasure. So yeah, so then we will see you after New Year. So Happy New Year and Merry Christmas.
Okay.
Bye bye.